Hello and welcome to the presentation on OPC UA for Surface Technology. My name is Peter Turczak, chairperson of the joint working group between the VDMA and the OPC Foundation and also managing director of the company Viva Wilhelm Wagner in Germany. You might ask yourself, what does the Surface Technology Initiative do? We are a group of companies organized in VDMA and the OPC Foundation working to creating a so-called Companion Specification for the use of OPC UA in surface technology. Surface technology is quite broad in its meaning, as functional and aesthetical modifications are done to virtually all surfaces of products. This includes cleaning, abrasive technologies like blasting, coating with liquids or powders, and even plasma-based processes that your glasses get their finish with. So as a team, we provide process technology to nearly all industrial sectors like automotive, optics, aerospace, and even food and pharmaceuticals, to name just a few. Looking at the paint application plant, you can see there is a lot going on. We have pre-treatment, drying, paint application stages, sometimes multiple times, depending on your workpiece and the intended use. I don't want to go on all detail here, but obviously this goes beyond what used to be a tin can with paint and a brush to apply the coat on the object. The current focus of our working group is on the material supply system. This takes care of preparing material for application with mixing and pressurization and delivering it to the application system, like a spray gun operated manually or a robot-mounted spray nozzle. This already goes beyond classical paint application processes, as gluing, filling, and so on basically have the same structure from the material supply side. Here you can see the current members of our working group coming from various backgrounds like classical paint plant engineering, but also from material supply industry. Furthermore, we are happy to have the academic institutions, software companies, industry consortiums, and trade show organizers as our partners. If you, after this talk, consider participating in our working group, we are happy to accept new members of VDMA or OPC Foundation as full members. Other companies can join as guests and can provide input and engage in discussions. These guests do not have a vote in case decisions have to be made by a majority vote. Look at what standardization did in the beginning of the Industrial Revolution, where screws, bolts, nuts suddenly became standardized. USB had a big impact on the usability of computing. Today, you can plug in virtually any device into your computer without hassling with drivers, configuration, and so on. Therefore, integration of parts into systems is greatly simplified, which also speeds up the startup times in complex scenarios. Standardizing parameters is the next logical step in this journey, as a set of predefined parameters that represent best practices will immediately eliminate discussions on problems already solved. Focusing on a project with specific customization is much simpler this way. An example from my own experience here. A consortium of 6 European companies built a plant in Chile. Despite of several phone calls resulting in specification documents, it took programmers and from all companies on site about 6 weeks to finally start up the system and iron out all the misunderstandings on the interface definitions. Having a predefined framework to start from would have saved every company valuable developer time. The process communication inside a process plant can be very, very complex. Here you can see the data path between different entities inside the plant. Going from bottom up, we see the peripheral systems like technical ventilation and conveyor systems supporting the whole process. The individual processes shown in the systems layer contain steps that involve various machines that communicate with each other, like measuring and handling equipment, automated tools, and also manual process steps if necessary. We will look into the spray booth a bit more throughout the presentation, as the current working group focus is exactly on the paint application process itself. All of the processes are mostly supervised and directed from their respective section controllers shown on the machinery layer here. Data points are instructed to be fed into MES systems that provide quality and environmental reporting. So wrapping it all up, we see a lot of communication going on between various partners that has to be managed in an appropriate way. Having all these systems cooperate with each other, you will see various vendors, Siemens, Allen Bradley, Omron and Fanuc and whoever, with their own control systems, their own protocol stacks. All of those have to communicate one way or the other Back in the day it was pretty simple. You just hooked up some 24-volt I/O controls and just sent like 24 volts over that, and if the 24 volts was present, it was good. If not, the signal was deasserted. Simple, elegant, well, mostly, but not for variables that contain like floating point information. So our approach was to model it in the OPC UA environment, and having such a complex and diverse ecosystem around us, it was not an easy task to do. So we choose the following. First of all, we identified the relevant machines involved. This is actually more complicated than you think, we will see in the next slides. Second, we chose a topic for our first companion specification, the material supply system, as those are most likely the core of a paint application system. And third, we defined use cases for horizontal and vertical communication. Horizontal being machine-to-machine communication, like managing production processes between subsystems, like applying paint and flushing the paint system afterwards. Vertical being MES and data mining, aimed at, for example, quality or environmental reporting. Fourth, we want to integrate customer needs by looking at specifications from past projects, relying on information and best practices, but also this will come more into focus as we progress in our companion specification and start field testing it. Also, end users could join our working group in order to let their voice be heard directly. Fifth, the integration of other working groups is important to us, as there are many places where we can already benefit from progress made by other working groups, and we could also provide our information to others. We will see more about that also in the next slides. In this slide we show the machinery and the hierarchy of the companion specification involved in the paint application processes. As we can see, the machinery companion specification will provide kind of a bracket around all the subsystems we specify. For example, the cleaning and the pre-treatment will have their own companion specifications later. The orange boxes represent companion specifications, while the darker blue ones stand for aspects within those. Light blue boxes shown are the companion specifications or aspects thereof we do not want to specify on our own, like for example pumps and motion devices. Looking at the use cases we defined, those are, first of all, the quality assurance and traceability use case, which will provide time-stamped raw data for high-level systems like MES. Data transfer between components, as in use case 2, is also within our scope. This is aimed at machine-to-machine communication for improving interaction between systems working together in a process. Now we're taking a step back and looking at the big picture of the other working groups and touching points with those. This slide shows the progress of other departments within the VDMA and their respective progress in creating their industry-specific companion specifications. Now we show you the interaction between our working group and others. Labeled in red, we see working groups that will benefit from what we specify in our systems and will involve surface technology equipment or similar components. Highlighted in green, you will see working groups that provide building blocks used in surface technology and therefore will provide object definitions we could benefit from. This is also the benefit of having the OPC Foundation and VDMA working closely together to bring best practices from the industry directly into the specification processes. In order to make our modeling more comprehensive, we defined 4 basic elements we can use. Instantiable objects, in green, are meant to be used by users of our companion specification for modeling their own processes in real-world plants. These are high-level building blocks included into end-user system models. In blue, we represent objects to be used within our specification to model instantiable ones. These objects are not intended to be used by end users. Properties in yellow are immutable read-only information stored on a device which represents static data like technological system information such as limits, but also user manuals and whatever does not change over the lifetime of a product. Finally, parameters, shown in orange here, represent process variables that consist of at least one read-only part, like a sensor value, and optionally a read-writable set value for process control. Now we can see an overview of the object hierarchy we have defined for a material supply system within our working group so far. As you can see, this is a very complex system and every subsystem itself contains its own instantiable top-level classes. In this slide we will look at how we modeled a valve. In our mind, an instantiable object contains at least three things. First, metadata, second, state, and third, process data. Metadata specifies the name, physical location, parameter limits, and administrative information, and whatever is needed for planning, validation, and operation of the unit. Second, there is state, which we consider a basic and mostly abstract representation of a machine's state for dashboard or cockpit views, in order to reduce information to manageable limits and be the same among all participants within the system. Third, there is process data, which is, in my opinion, the most juicy thing in the whole system. It is very important for managing a process and also documenting it. Therefore, we can use it for control and quality purposes and predictive and preventive maintenance. Also, this is relevant for machine-to-machine automation, where process data from the previous step in a multi-stage process can be used to guide the following steps. Here you can see the current specification representation in a tabular form. The position in the modeling tree we defined earlier is visible as a dotted number form in the left. It is important to understand OPC UA allows us to create nested structures of mandatory and optional objects. This allows for conditionally mandatory information, like for example when you have a liquid coating, you might have information like volatile organic compounds, VOC content, which might not be relevant in a powder coating system. Therefore, you can arrange your objects in a way that to have the VOC content mandatory if you're describing a liquid paint process while not having it at all in a powder coating process, depending on how you organize your object hierarchy. Now the question arises, who will orchestrate all the elements in a paint application process? Because as we started out, we wanted to make it easier to orchestrate the complete system and make it simple to bring up the system made from elements that might be delivered by vendors from all around the globe. But also we found out, like in a good concert, it's not only made up by good musicians, but also the timing is vital. Therefore, it is very important to clearly define roles and sequences of processes that all components have to adhere to. But being in such a diverse environment makes it very hard to simplify things. In some situations you have a process that comprises only of an application system, which might be as simple as just a spray gun, and a paint supply system that might only be a pump. But sometimes you have much more complicated systems, like the one we show here, and this is the most complicated system we could think of. We have an MES sitting on top of machinery being like cleaning and pretreatment systems, a spray booth, a paint dryer. These in turn contain measurement equipment, motion and handling systems, and so on and so on. This makes for a very complicated system. Now the question arises, how to make all these widely differing systems cooperate in a proper way. In a big system, you could use the information from the application system, like a robot, in order to control the paint supply system, which in turn could inform an ERP system to procure more material. But this would lead to a dilution of responsibility among all the actors in such a system, and therefore ultimately lead to problems that are very hard to troubleshoot, and changes in process layout would likely to cause changes in all other data bindings within the whole system. In order to make the process scalable, we envisioned a different way of controlling and directing the plant by introducing a new role we call controller. That controller contains the process knowledge, whereas application and paint supply systems do only have to do their part and do it right. The controller does not have to be a part of the machine, but is a role that can be shifted or delegated depending on the project size or even change over time. It is the controller's responsibility to provide all the necessary information of what to do and when to do it to all the application participants in the system. This example shows the flushing process of a spray plant, removing the currently loaded coating material from the system. This might be due to another color to be applied or due to shutting down the plant for maintenance. In our example, we only show the interaction between the controller and application and supply system, whereas it could be vastly more complicated in practice. At first, the controller tells the application system to prepare for flushing, which means that it should finish its current operation and return to a given point for flushing, which most likely is away from the workpiece and most commonly into a waste container. Also, the paint supply system is instructed what flushing materials to be used and their respective mounts. When both application and supply system have confirmed their respective completion of preparation, the controller goes on starting the actual flush process steps, always waiting for the supply system to confirm the amount of cleaning agent to be delivered. Therefore, we synchronize the flushing process between all the system partners, taking clues from the participants relevant in a certain step. So coming to the lessons learned, in our industry it is important to both combine vertical and horizontal communication, as both are very important to our end users. We also recognize that we have to orchestrate the communication between machine to machine, as we have a very diverse spectrum of machinery and their interactions, and this is very project specific. Therefore, we cannot have like a one-size-fits-it-all approach in order to link everything together and chain everything up. And we also try to provide more information to other working groups, especially the machinery working group, as there are so many parameters that seem to be very common between several systems, where it would be a lot easier if everybody spoke kind of the same language, which is the basic idea of the OPC world altogether. So coming to the next steps, we're just about to prepare a prototype. Once the prototyping stage is finished, we want to go into hardware integration and do real testing with real hardware, which will be a very interesting part of the journey, and we hope that most participants will contribute parts to that system, so we can show a big system of various manufacturers working together in unison. When the hardware integration is finished, we want to publish the release candidate, because we want to validate the specifications we did in a test field with, as I said, several participants, in order to make a good and viable product to ship out and to have commented on, and not something that is just on the whiteboard and hope that everything will be right. Yeah, thank you for your attention. Have a good day, and hope to talk to you soon.